Nah. Welcome to all the viewers. Myself R.Vetrivel, Unacademy Physics Plus Educator. Welcome once again all. Today we are going to discuss the important capsule concept of wave optics. Right? It will be very helpful for all the aspirant who is preparing for CET, JEE and NEET. Right? So in this pandemic period, it's the best to subscribe Unacademy, India's topmost online platform for coaching and teaching. So comprehensive batch is live on Unacademy for complete syllabus preparation. So it will be an affordable price, batches for complete preparation, quiz and periodic test with self-analysis, daily practice paper, full-length mock test with analysis, everything single subscription for unlimited access. So to subscribe, here are the plan. You can try for even a month plan for rehearsal. You come to know the difference, right? 6-month plan and 12-month plan is there. I appeal all to the viewers, use my code VETRILIVE. It is in descriptive box, right? Use my code to subscribe Unacademy plus subscription and enjoy the learning. Yes, today let us move to the wave optics. I am going to discuss the main concept of young double slit experiment. Right? In this concept only, maximum in all the competitive examination you will get objective type. So we all know young double slit experiment, it is interference happening, right? When two or more light waves travel in the same direction, right? superimpose on one another. As a result, there is a bright, dark, bright fringes obtained on the screen. Right? That's only interference. The energy is redistributed during interference. Right? Interference of light confirm wave nature. Right? We all know that about interference. Better example is the light beam produced by laser. Laser beam is a monochromatic light which can produce easily the fringes on the screen. Monochromatic light means we know interference taking place with the help of monochromatic light. The two sources must be a monochromatic, having same wavelength frequency. Most important is constant phase difference or zero phase difference. Right, that is the main condition for obtaining fringes on the screen, interference. If the sources are independent, right, they will not form, they are not suitable to form interference fringes. That meaning, if the two sources are independent wave, right, we cannot obtain interference. So interference, here you can see the two slit, distance between the two slits small d, distance between screen and slit is capital D. We all know that is a center point. From the two sources, the light wave reaches at point O or in same phase, right, equal distance. So you will get maximum brightness at the center. As we go higher, consider a point P. At this point, S1P and S2P are not equal. There is a path difference. So if you want to obtain fringes, bright fringes at point P, which is at a distance x from center O, we have the formula. If you want to obtain at point P the dark fringes, we have the formula. We all know first fringes, a bright dark fringes obtained mean the distance between any two consecutive dark or bright fringes are called fringe width. We know that fringe width equal lambda d by small d. Each letters we know. If this entire arrangement, this is N double slit experiment, Thomas N used this experiment to explain interference pattern. The whole apparatus is immersed in a water having refractive index. Then what happened? Fringe width beta reduces, right? So this fringe width related we are going to discuss today the important MCQs which are very helpful for all the competitive examination. Just to have an idea, location of fringe, already we know fringe mean we are on the screen, bright dark with equal space, continuously it appears, right? Fringe width mean that is beta, the distance between any two consecutive fringes is called fringe width. Now, location of fringes, as I said here, suppose in this N double slit experiment, right, this is central maxima. If I consider the point P on the screen at a distance x from the center O, if I want to get the maximum brightness, right, and minimum, maxima, minima, that's only this formula is given. First one, see that if you want to get position of nth bright fringe, that means I want to get 8th bright fringe at a point P, or if I want to get 3rd bright fringe at point B from the central maxima, this is the formula, x to the base n equal n lambda d by small d, right? This lambda d by d is beta, right? Fringe width. So the nth position of dark fringe if you want to get, right, from the central maximum, we know that this is central maximum. C is the central maximum at point P, which is at a distance x. If I want to obtain central maximum, formula. If I want to get central minimum, that means dark fringe, that's the second formula. If I want to get the position of nth dark fringe from the central maxima, x to the base n equal 2n minus 1 into lambda d by 2d, right? So 2n minus 1 lambda d by d is beta. So 2n minus 1 into beta by 2, where n is, we know the integer. So this formula keep in mind in order to obtain nth bright fringe on the screen or dark fringe on the screen. These formulas are very important. Now based on this concept, let us see the problem, right? Here is the problem, first one based on this concept, right? Excuse me. See the first one. Two slits are separated by a distance of 0.5 mm and illuminated with the light of wavelength is given 6000 angstrom. If the screen is placed 2.5 meter from the slit, so capital D is given, wavelength is given. Two slits are separated by the distance 0.5 mm, small d also given, distance between the slit. The distance of the third bright fringe from the center. Question C, number of bright fringe n equal to 3. Distance of the third bright fringe. Remember now, distance of the third bright fringe. Right, at point P, if you want to obtain third bright fringe x3 from the center, right? This is only the question. So bright fringe, see that formula, nth bright fringe, x to the base n equal to n lambda d by d. Here n is 3, that's it. So bright fringe if you want to obtain, right? So see that now, distance of the third bright fringe from the center. So distance of nth bright fringe from the center, we know the formula, xn equal n lambda d by small d, right? So here third bright fringe, so x to the base 3 equal to n equal to 3. So 3 into, what is wavelength is given? 6000 into angstrom given, 10 power minus 10 meter, convert angstrom into meter, into capital D, distance between screen and slit, 2.5 meter, SI unit given, directly go ahead. Small d, 0.5 millimeter given, convert into meter, 10 power minus 3, simplify, you will get 9 into 10 power minus 3 meter. Answer all you see that given in millimeter. So 9 millimeter. So correct option now, option D. Yes. So keep in mind this. Third bright fringe from the center. Let us go for the next sum. Here it is. See here in young double slit experiment, capital D equal to 2 meter, directly given, distance between the slit and screen. Small d is given, distance between the slit, and wavelength also given in angstrom. Then fringe width and the position of third maxima. Again, third maxima. Understand the question. First course they ask fringe width. We all know fringe width beta equal lambda d by small d, right? Fringe width, that is equal lambda, wavelength we know that 6000 angstrom, angstrom convert into meter into 10 power minus 10 into capital D is given, distance between the screen and slit is given to by small d, it is 6 millimeter, convert into meter, 10 power minus 3, right? So you will get 0.2 millimeter. This is the fringe width. First question over. Now the position of third maxima. Position of third maxima. Position means distance. Xn equal n lambda d by small d, position of third maxima. So x to the base 3, n is 3 equal 3 lambda d by small d. As we know, lambda d by small d is nothing but fringe width, right? So this, or I will write as a beta, right? This is 3 into beta, that's all. So 3 into what we got, the fringe width 0.2. So you will get 0.6 millimeter. So first option is correct, right? Already we got fringe width beta and third maxima. Yes, let us go for another concept now. So far we discussed the concept of nth position of bright and dark fringes, maxima, minima, right? We discussed. Now let us go for, right, one more. See that in a n double slit experiment, two coherent sources, we all know, interference pattern want to take place mean the sources must be coherent source, right? The two sources having same wavelength and frequency and zero phase difference or constant phase difference, then only we can say it is the coherent source, right? Coherent source required for interference to happen. So the coherent sources two are placed 0.90 mm apart, that means small d. Two sources are kept apart and fringes are observed 1 meter away, that is capital D, right? Small d is given, right? Small d is given 0.90 millimeter and the screen is kept 1 meter away, distance between slit and screen. If it produces the second dark fringe, keep in mind here, so far previous two questions we discussed bright fringe, right, maxima. Now dark fringe, second dark fringe, so n equal to 2, right? Second dark fringe at a distance of 1 millimeter from the central fringe. That means the distance xn also given 1 millimeter from the central fringe. From the center of the screen, the point P where the second dark fringe appeared, that is 1 mm. Okay. The wavelength of the monochromatic light used, as I said, we all know. The source, coherent source mean main requirement, the light must be a monochromatic light, single wavelength light, right? Okay. Now, dark fringe, as we all know, distance of the nth dark fringe, x to the base n equals distance of the nth dark fringe. Can you remember? Distance of the nth dark fringe, right? Can you see that? Distance of the nth dark fringe, 2n minus 1 into lambda d by 2d, right? Now you can use it, you know that formula, right? So distance of the nth dark fringe, x to the base n equal, we know that 2n minus 1 into lambda d by 2d, right? That is equal. Now substitute here, what is the question? Second dark fringe, so n equal to 2. Substitute now. 2 into n, 2 into 2 minus 1 into lambda d, right? As you keep it as a lambda d only, right? By 2d. Now simplify. 2 to 4 minus 1, we know 3 lambda d by, right, 2d. That's it. Now substitute all the values whatever given. We got now x2 equal 3 lambda d by 2d, right? We got x to the base 2 equal 3 lambda d by 2d. Now x is given distance, 1 mm is given. 1 mm, 1 into 10 power minus 3 meter equal 3 lambda, 3 into, what is it? wavelength we need to find into capital D 1 meter by 2D. 2 into D is 0.9 millimeter. Convert into meter, 10 power minus 3. You will get 6 into 10 power minus 5 centimeter. Option D is correct one. Right? Yes. Let us go for another one similar. Right? Minima, that means dark fringe we are discussing. How to obtain nth dark fringe from the center. Right? In N double slit experiment. In YDSE N double slit experiment, the slit separation is 1 mm, small d, and the screen is 1 meter away. For the monochromatic light of wavelength is given 500 nanometer into 10 power minus 9. The distance of third minima, minima in the sense we know, right? Third minima, that means dark fringe, maxima means bright fringe. So third minima from the central maximum. We all know distance of the nth minima from the center of the screen, central bright, is given by, we all know that formula, xn equal to n minus 1 into lambda d by 2d. This is the formula for obtain nth dark fringe from the center. Here according to question, for a monochromatic light of wavelength 500 nanometer, the distance of third minima, so n equal to 3. So distance of third minima, x to the base 3 equal 2n, 2 into 3 minus 1, right? Into lambda, wavelength is given 500 nanometer, 10 power minus 9 into capital D 1 meter, right? Divide by 2D, 2 into small d is given, right? 1 mm, so 1 millimeter convert into meter into 10 power minus 3, right? So you simplify this, you will get, this is 236 minus 1, 5 into 500, right? Into, check it now, 5 into 500 into 10 power minus 9 by 2 into 10 power minus 3. Simplify now, you will get 1.25 into 10 power minus 3. That will become 1.25 millimeter. So B option is the correct one. Right? Okay. Let us go for the next one. Right? Yes. Here, next, this formula you need to remember. Whenever a thin film, right, is placed in the path of one of the beam, see from the two sources, slit S1, S2, in any one of the path, you place a thin film whose thickness is small t. The optical path of the beam gets longer. The path difference is given by delta x is denoted as a path difference equal to mu minus 1 into t. The t is thickness of the film or thickness of the plate, whatever we are placing on any one path. See that the light rays come from the two sources, two slit. On one path you place, right, a thin film. Right, now what happened? The optical path of the beam gets longer. The path difference is, this is formula. Keep in mind, path difference. Refractive index mu minus 1 into t, where t is mu is refractive index, t is thickness. This formula remember. Then, if any one of the plate, instead of thin film, I am placing a thin glass plate whose thickness is small t. Thin glass plate I am placing on one beam. That means the path of the first one, S1 path I am placing a glass plate. Now, whenever the glass plate of thickness t is placed over one of the slit, then there is a lateral shift in the path, right? The lateral displacement is given by x equal mu minus 1 into t capital D by small d. So these two formulas very important. Based on this, now let us solve the problem. A thin glass plate is introduced, thickness is small t, then lateral shift or lateral displacement is given by mu minus 1, refractive index minus 1 into t, thickness d we know, distance between the slit and screen, and small d, distance between the slit. Yes, we know now these two formulas. Let us go for the first problem based on this. Yes, in Young double slit experiment, if N1 fringes are visible in the field of view with the light of wavelength lambda 1, when N2 light of wavelength lambda 2 and the same field, then this concept also understand. N1 lambda 1 equal to N2 lambda 2. Suppose number of fringes, N1 fringes are visible in the field of view when the light I am using wavelength lambda 1. N2 fringes are visible when I use the wavelength lambda 2 in the same field. Then N1 lambda 1 equal to N2 lambda 2, or N1 by N2 equal lambda 2 by lambda 1. So this also keep in mind, N1 lambda 1 equal to N2 lambda 2. Yes, based on this, now let us see the problem. Yes, in a transparent medium, right, the refractive index is given 1.5, thickness 2.5 into 10 power minus 5 meter inserted in front of one of the slit. In one slit we are introducing, right, thickness is given, right, a transparent medium, refractive index given, a thickness of t is inserted, right, any glass plate you are inserting, thickness is given in one of the path. How much will the shift in the interference pattern on the screen? Interference pattern, there will be a shift in the interference pattern on the screen. The distance between the slit is given, small d, 0.5 mm, and the between slit and screen is 100 centimeter, capital D is given. So question is lateral shift. In one of the path, right, the two slit S1, S2, right, in this on the screen, right, one of this path you are placing a glass plate of thickness T. What is the lateral shift? We all know, just now we discussed, lateral shift equal mu minus 1 into small t capital D by small d, right? All is given. Refractive index of the glass we know 1.5 minus 1, as we know refractive index of glass 1.5, right, minus 1 into t, thickness is given already 2.5 into 10 power minus 5 into capital D 100 centimeter, convert into meter into 10 power minus 2 by small d 0.5 millimeter, convert into meter, so divide by 1000, that is why 10 power minus 3, simplify, you will get 2.5 centimeter. It is the shift we can observe on the screen, 2.5 centimeter it is shifted, right? So lateral shift, we got it. Now next, see here, in a Young double slit experiment, 12 fringes are observed to be formed on the certain segment of the screen. So the number of fringes observed on the screen is 12, N is given. When light of wavelength 600 nanometer is used, if the wavelength of light changed to 400 nanometer, so number of fringes 12, wavelength lambda 1. If the wavelength you are changing 400 nanometer lambda 2, then what is the number of fringes observed on the screen? As we know, right, N1 lambda 1 equal N2 lambda 2, that's it, we know very well, right? Here the question is, first N1 given, 12 fringes observed on the screen, wavelength is 600 nanometer, N1 lambda 1 is given. N2 is the question, number of fringes observed on the screen when the wavelength used is 400 nanometer. So from this, N2 equal N1 into lambda 1 by lambda 2. Right, that's it. So we know n1 12 into lambda 1. Right? 600 by 400. That's it. You will get number of fringes. N2 will be 18. Is the correct answer. Yes. Let us go for the next one. Here it is. In N double slit experiment, the aperture screen distance is 2 meter. The aperture screen distance is 2 meter. The slit width is 1 mm. Right? Slit width means small d. Light of 600 nanometer, lambda 1 is used. If the thin plate of glass refractive index we know, of thickness small t is given 0.06 millimeter is placed over one of the slit, then there will be a lateral displacement of the fringes. How much? Right? As we all know, right? In the double slit experiment, S1, S2 is a screen, right? When both any in the path, any one of the slit you are placing a thickness of, right, 0.0 mm thickness of glass plate you are inserting on one of the light way slit, then how much lateral shift, lateral displacement by fringes on the screen will be shifted by how much? As we all know, right, whenever we insert a glass plate of thickness small t, right, we know that the lateral displacement in the fringes x equal mu minus 1 into small t capital D by small d, right? Here mu is given 1.5. We know refractive index 1.5 minus refractive index of glass plate, glass 1.5 minus 1 into t. Thickness, see that, thickness of the plate, how much is given? Thickness of 0.06 millimeter. So 0.06 I can write 6 into 10 power 5, right? So we can able to write it 6 into, right? So see that, substitute yes, 6 into 10 power 5 minus 5 I can write, right? Millimeter convert into meter, 10 power minus 3, 0.06 digit move, 10 power minus 5, 6 into 10 power minus 5, t into capital D. Capital D is given here 2, see that, 2 meter, right? Okay, divide by, what is small d? Right, slit distance is given, right, 1 mm, 1 into 10 power minus 3 meter, that's it. So you will get the lateral displacement as 0.5 into 12 into 10 power minus 2. You will get 6 centimeter is the correct option, right? So option B is correct. If we substitute lateral shift formula, remember lateral displacement, whenever a glass plate or any other material, when you insert in one of the beam, right, either S1 or S2 path, if you insert, then there is a shift in the fringes on the screen. That's only lateral displacement, X, this formula, you will find it. And next one, in Young double slit experiment, right, the slits are 2 mm, small d, illuminated by photon, light of wavelength lambda 1 given, lambda 2 is given. At what minimum distance from the common central bright fringe on the screen 2 meter, capital D is given. The slit will be brought bright fringe from one interference pattern coincide with bright fringe from the other. That's the meaning. We know that here n1 lambda 1 equal to n2 lambda 2. Remember, so n1 by n2 equal lambda 2 by lambda 1. What is lambda 2? It is 10,000 by 12,000. You will get 5 by 6. n1 by n2 equal. Now n1 what? Minimum. n2 maximum. Right? So remember, n1 it is minimum, that means dark fringe 5. n2 is maximum, bright fringe 6. Right? Then what is the question they asked? We see at what minimum distance from the common central bright, right, on the screen, right? So question is x distance minimum, right, on n double slit experiment from the central bright. This is S1, S2, this is the distance B, this is xn from the center O, right? Both waves will reach here. Now x minimum equal, we know that formula, x minimum n lambda d. So here n1 lambda 1 by small d. That's it. All values given. All values given. n1 is given 5. n lambda 1 is given, right, 12,000. Capital D 2. Small d is given. Substitute. We will get 6 into 10 power minus 3 meter. That is nothing but 6 millimeter is the correct option C. Right? Come to the last one. Right? A mixer of light consisting of wavelength lambda 1 nanometer and unknown wavelength. Another is lambda 2. We unknown. Lambda 1 is given. Another is unknown wavelength. Illuminates n double slit and gives rise to two overlapping interference pattern on the screen. The central maximum of both light coincide. Further, it is observed that third bright fringe of known light coincide with the fourth bright fringe. See, third bright fringe coincide with fourth bright fringe of the unknown light. So from this data, wavelength of the unknown light, don't confuse, very simple. It is given n1 lambda 1 equal to n2 lambda 2. That's it. n1 it is given 3. Lambda 1, first one is given wavelength 590 equal. n2 is a 4. Fourth bright fringe of lambda 2. We don't know the wavelength, unknown wavelength. From this lambda 2 equal, we will get 442.5 nanometer. Option 3 is the correct one. Right? So that's the end of today's session. I hope today in n double slit experiment we discussed the important concept, right? Similarly, many more you can, right, detailedly you can watch if you subscribe Unacademy Plus course, right? Already champion coach is on the line. Champion batch, comprehensive batch is already in progress for complete syllabus preparation. So I appeal to all the viewers, subscribe Unacademy, use my code R.Vetrivel, and you will be the topper in your competitive examination. With that, right, myself R.Vetrivel, Unacademy Plus educator, signing up from you all. We will meet you the next YouTube class. Till then, have a nice day.